So LiDAR enhanced forest inventory demystified. It's something that's been done for a lot of years now, and I don't know that it's all that mysterious, but I think that it's certainly more complex than just generating a bare earth digital terrain model from a LiDAR point cloud, for example, or a canopy height model, or some of the more direct derivatives that you can create from actual, just point cloud data. So we want to talk a little bit about that, and just to set the stage and make sure that we're all on the same page. We'll just start with some of the basics. So, how does LiDAR work? Well, really, it comes down to all of these sort of a convergence of technologies that have been developed over the past, I would say, maybe 20 years or so, maybe a little longer than that, where you had the advent of airborne GPS and very accurate airborne GPS inertial measurement units within the aircraft, where you can measure the instantaneous orientation of the aircraft while you're shooting these laser pulses down to the ground from the aircraft from a LiDAR machine. So you had this convergence of technologies come together where we're able to measure with very, very high accuracy and precision that the X, Y, and Z, or elevation above sea level, of these billions of points of LiDAR pulses. So that's really the name of the game. And if you're able to do all of this with high performance computing in the aircraft, you're able to piece this together and again capture these returns from LiDAR pulses with very, very high accuracy and precision. I like to think of it, in this graphic sort of does a good job of this, is you're just shooting lasers out of the aircraft, right? And you're literally like painting the ground with these LiDAR pulses, something on the order of 500,000 pulses per second out of a standard, sort of a traditional discrete return LiDAR machine. So pretty amazing technology when you stop and think about it. And so each of the initial returns of a LiDAR pulse, you're going to get up to 4 or even 5 returns with sort of the traditional discrete return LiDAR machines. So the first return is typically the top of anything, right? So the top of a building, tops of trees, things like that. And then each of those pulses sometimes will partially hit, say, the top of a tree, but then another portion of that pulse will bounce off of the mid canopy and the lower canopy. And if there are enough gaps in the forest canopy, for example, you'll end up with returns from the ground, right? So that's why it's typically referred to as, discrete return, multi-return LiDAR. And so what does that look like when you actually do the post-processing? And the vendors that fly LiDAR and acquire LiDAR, you're talking about hundreds of billions of points, depending on your mission and your area of coverage. So there's a lot of calibration that goes into the process, data calibration, and then also a lot of post-processing, data cleanup and calibration, and data classification, point classification, all those sorts of things. So there's a lot that goes into it on both the before the acquisition and also after the acquisition. But you end up with this 3-dimensional point cloud, right? So every one of these points, these are colored by elevation. So the ground points are basically a cyan color in this graphic, and then the tops of the trees are orange to red, right? And each one of these points has a very accurate measurement of X, Y, and Z of its actual position in space. Just another couple of examples here of these point clouds. And you know, this is a pretty dense point cloud here. I don't know what the actual first return density is, but you know, it's pretty high. So the higher the density of the point cloud, you know, the more points you have, which therefore allow you to better measure and characterize those features on the surface of the Earth that you're interested in mapping in a 3D point cloud, right? So both of these are good examples of just this really dense point cloud, and you can even make out, you know, some of these trees, you know, probably like white pines have that characteristic white pine look to them. The other nice thing about LiDAR point clouds is it's an active sensor, so it generates its own energy source, and then again records returns from those LiDAR pulses. So the points actually penetrate the canopy. Whereas you can do this with photos and something called structure from motion, but you're only able to generate a three-dimensional point cloud from photos where you actually see, you know, what you see in the photograph is what gets generated for the point cloud. So you're not able to see down into the shadows in a photograph, whereas with a LiDAR machine, you're getting returns in that mid-story and down into the canopy of the forest, which is very important, particularly with trying to model forest inventory parameters like we're going to talk about this afternoon. And then for each one of these points, you know, you've got a lot of information that is provided when a vendor provides or delivers a three-dimensional point cloud, where every one of these points has, you know, its intensity value, if it's been classified, its classification, and its return number. All of these things are something that you can query in a GIS for every point in a LiDAR point cloud. So I've already mentioned that this is a lot of data that we're talking about, right? So if we just look at, for example, the Allagash Township up in northern Maine, it's a little under 84,000 acres in size. And this is just from the state LiDAR, the QL2, so the free stuff for the state, you know, 3 to 4 first return pulses per square meter. That works out to about 1.4 billion points. And the Allagash is encompassed within 344 LAS tiles. So the LAS is just the file format, sort of a standard file format for point cloud data. And those are 1 kilometer by 1 kilometer tiles. Sometimes they're 1.5 by 1.5. So, you know, a few hundred LAS tiles, 1.4 billion points, you know, over 5 gigs in size just for the Allagash, right? So think about that if you just expand it to, well, I want the same thing for the entire state of Maine. Obviously, you know, you're talking about just vast amounts of data. And that in and of itself is a real challenge, and certainly is a challenge as part of enhanced forest inventory. So we'll talk more about that. So there's sort of two, I think in general, most people think about two categories of what you can do with you know, LiDAR-based point clouds. Certainly you can generate things like digital terrain models, and that's something that's, you know, really very easily done in a GIS with a point cloud. Canopy height models, also something very useful, very easy to generate just within a GIS from your point cloud data. And then various height metrics, you can do that as well, measuring things like crown area and canopy density. All those things are sort of basic derivatives. You're actually, you know, taking these measurements directly from the point cloud data itself. What we're going to focus on this afternoon is more what you can do from a modeling perspective. And there are lots of things that you can model with derivatives from LiDAR data. Terrain modeling, things like hill shades, certainly slope and aspect layers, those sorts of things. And then all of your standard hydrography modeling, you know, generating flow accumulation rasters and stream networks and delineating watersheds. all of that type of stuff is very easily done with more or less standard tools in a GIS. Water table mapping, this is something that the folks up in Dr. Paul Arp and in his shop up at the University of New Brunswick, they've sort of developed this fairly sophisticated process for taking high resolution digital terrain data, typically generated from LiDAR, but also photo-based terrain models as well, with photo-based point clouds where that's appropriate. But start with that resolution DTM from LiDAR and do your standard hydrography modeling workflow. But they also incorporate things like soils and other types of, they like to use the term their secret sauce. So they don't really talk in too many details about the additional aspects to what they do in their modeling. But they do start with, this high resolution, LiDAR-derived, typically LiDAR-derived digital terrain model for the water table mapping. And that's really impressive. If any of you have seen some of the data that they have produced with their process, these depth to water table maps, wet area maps, it's really quite impressive. And then just, general site productivity and characterization, those sorts of things are commonly done with point cloud data from LiDAR. And then what we'll focus on again this afternoon, and I'm going to demo here in a minute, is what we can do with modeling forest inventory attributes using point cloud data and field plots. So things like basal area, volume, biomass, those sorts of things. All right, so, in general, you're in a LiDAR point cloud, your last return is typically at the ground. Your first return, as I mentioned earlier, is basically the tops of the trees, or whatever that first object is that, an incoming LiDAR pulse hits. So it could be the top of a building, could be the top of a vehicle, could be a bird. Sometimes you'll see that in a point cloud where you'll have, basically the tops of the forest canopy and then something that, you might say is an outlier, but it also might be a bird. I mean, that's, you're literally shooting lasers, up to 500,000 pulses per second. So there's a lot of laser pulses that are, coming out of that LiDAR machine, and sometimes you'll just hit a bird or a plane or maybe a drone, right? So there could be a lot of things that could give you that first return from an initial LiDAR pulse. Okay, so kind of shifting gears to think about this more in terms of enhanced forest inventory and how this works. Typically what we'll do is, first of all, flatten the point cloud. So basically, remove the ground so that the ground points are at an elevation of 0, right? And then everything else is height above ground at that point. So that's the first step typically. And then you've got a series of plot data that's been collected, out in your forest with measurements of things that you want to predict throughout your point cloud, right? And so you'll clip out these plots from your point cloud data. And typically what you're doing is you're generating what are called, most commonly referred to as grid metrics or standard metrics, where you're just measuring height and density descriptors of the point cloud itself, and you're rasterizing those, and then you're clipping those out for each of your plots. So things like, the mean height, the various percentile heights within your point cloud data, what's your maximum height, skewness, standard deviation, what's the variability within your height and density metrics. So all of these, and there's a whole long list, there's hundreds of these metrics that can be generated and in sort of a gridded form within your point cloud data. So you start with that, and then basically just build some models. And random forest is one of the most common machine learning algorithms that are used to build these relationships between your plot data and the LiDAR metrics that are sort of characterizing or measuring height and density within the point cloud. And then you're able to predict things like basal area, and volume, and biomass, so on and so forth. So we typically refer to this as an area-based approach. You know, you've got your traditional stand level inventory. Let's say you want to generate an EFI, you know, with a 20-meter ground sample distance or spatial resolution. You've got your point cloud data with, you know, billions of points in it, and then your ground plots. And again, you're just, you know, you're generating these raster LiDAR metrics, and then you're clipping that out using your plot data. And then you're building those models typically with something like random forest. That's not the only modeling approach that's used, but it is probably one of the most common that's used. Pretty easy to understand, very easy to implement in something like R, which you'll see in a minute. And then you can generate these, you know, these models and then apply them to, you know, the entire area of interest where you have LiDAR data for. So in a nutshell, that's how that works. And then of course you can summarize, you know, each of your prediction maps by your initial stand level inventory, right? So you can characterize and summarize at the stand level after you make these predictions on a grid basis, for example. So just some more examples there. So again, you know, your inputs are your field data, your plot level grid metrics, LiDAR metrics, and then your metrics across the entire ownership. So you build these models in something like random forest, and then you apply the model for the entire area of interest. Okay, so I want to spend a couple of minutes before we get into the demo just talking about a little more of the details involved in the basic workflow, but also some of the challenges with doing LiDAR-based EFI. So you know, basically whatever you want to model in an EFI approach, you need to measure that in the field on the plots, right? So that's key, and it's best to do that and summarize it at the plot level. That's sort of where you need to get the data. The plot level data is at the plot level, and measure the things that you want to try to model with random forest, for example. So accurate calibration plot locations and good measurement techniques in the field are very, very important, because again, you're clipping out these plots from the LiDAR grid metrics. And if you just look at a scenario where, well, can I use, you might ask yourself, can I use, you know, just a garment to locate my plots? You can, but you know, as with most any modeling approach, you know, the quality of your input data, you know, speaks to the quality of your results. And we've done this with some Garmin plot data, and have achieved mixed results, to put the best possible spin on it. And you know, anything beyond predicting something like percent softwood, you know, with recreation or consumer grade GPS located plots is very, very challenging, and often you end up with rather poor results. On the flip side, using survey grade accuracy with your plot data locations, you can achieve very good results. There are other factors that go into this. You know, how dense is your point cloud data? So the standard QL2, you know, state LiDAR is not the densest, and it's also leaf off. So those are a couple of challenges with using the statewide data. The free stuff for this type of work but we have done it and achieved some rather good results when you're able to have plot data that has been collected with survey grade GPS. So that, I would say, is really key. The other thing is we've tried this with variable radius plots, with prism plots, and then of course with fixed radius plots, and you know, pretty uniformly have achieved better results with fixed radius plot data that has been located with survey grade GPS. So those are really, really important. And then, so, you know, again, you're building these relationships between your plot data, which we looked at just a couple of slides ago, and then your height and density metrics, right, from the LiDAR grid metrics, where you're measuring that point cloud, the elevations, the densities, LiDAR intensity, just that's a reflectance of the laser pulses. They're near infrared laser pulses from most LiDAR machines. Bathymetric LiDAR typically will use a green laser, but everything else is typically a red near infrared laser. So then you get these metrics, and again, I've mentioned, you know, there's hundreds of these, and so you're just building those tables of, you know, plot data located or joined with your LiDAR height and density metrics. I mentioned a couple of challenges, just the point density of the state QL2 LiDAR at, you know, say 3 to 4 first return pulses per square meter is not the greatest density for enhanced forest inventory. You know, things on the order of 6 to 8 pulses per meter or greater or higher, you know, typically produce the best results. But you can achieve some fairly good results even with QL2 LiDAR. One of the things that we've discovered in some of our work with some of our stakeholders, so this is from some work that we've been doing with Basque-Kehegan Company, you'll notice that the kind of split down the middle, the graphic on the right here, you know, you've got fewer points in your point cloud on the left-hand side of this graphic and many more on the right-hand side of this graphic. And you can't see the LiDAR data collection map on the graphic on the left here, but these are, you know, the table, the legend here is all these different flight-lined missions with different dates where they were collected. And that's the important thing to keep in mind here. So, you know, you're not going to fly, you know, these large areas all in one day by any means. And you need conditions to be right, right? You can't have snow cover. The goal of the initial campaign of LiDAR for the state was to get a very accurate digital terrain model. So leaf off was what was one of the requirements for this initial LiDAR data collection for the state. And sometimes you got that, sometimes you didn't, just depending on, you know, leaf out in the spring and when the leaves fall off the trees in the fall. So what you have on the point cloud here on the right is basically where trees are beginning to leaf out late May and into June. And then on the left-hand part of the graphic, the point cloud graphic, leaf off, right? So you're dealing with those kinds of challenges as well, you know, when you're using the best available LiDAR rather than, you know, having a vendor go out and fly it for your own particular project. Obviously, you have more control when you're paying for the LiDAR. The LiDAR is very expensive, so that's something that that is often avoided if possible, right, for obvious reasons. Before I start walking through a demo of sort of the workflow that we've developed in R for enhanced forest inventory, I'll just mention a few resources, and many of you, probably most of you, are already aware of these. So the national map you can get through the USGS 3-DEP program. You can get LiDAR point cloud data and all the derivatives. So there are many derivatives that you can get as well from the point cloud data, so that's available, and that's a great resource. The other that I would mention is the NOAA Data Access Viewer. So typically focusing more on coastal LiDAR, but that's a great resource as well, and they've got a lot of free point cloud data there as well. And then, of course, the USGS Earth Explorer. We're going to look at a LiDAR-only workflow, but it's very common to use optical imagery. So things like Sentinel-2 is something that we use very commonly when we do these workflows. And it really helps, particularly, as you might imagine, with modeling for software. So those are also, independent or explanatory variables that go into our modeling process in random forest. So that's just an additional input into the modeling process. So that's a great resource, the Earth Explorer, for getting various types of imagery to incorporate in these workflows. And then, of course, some of you know this, but the Canadians have been doing this for many years now, and they're always, in the literature and just operationally speaking, they've really nailed this. They've got it down, and it's a provincial level program in many or most of the provinces, national meetings that they have every year. And they do have a couple of publications that are commonly referenced in the literature, screenshots you see here, which are basically best practices guides for doing LiDAR-based EFI. We're currently doing a project with the Cooperative Forestry Research Unit, looking at, basically how to optimize the use of the state QL2 LiDAR for EFI. And we are planning to develop sort of our own main specific EFI best practices guide as part of that project. So it's an ongoing project. I believe that's going to wrap up next year sometime. But we've had some delays with the pandemic and grad student challenges, but hope to move that along aggressively this summer. So stay tuned for more information with regard to that. All right, what else would I mention? Suppose that's it for now. Any questions? And hopefully Dave and Dan have been keeping up with the chat. I'll take a look at that now and see if there's anything here we want to address. Any questions or comments before we move into a demonstration? All right, great.
Who's got, anybody have more questions? I'll just chime in because of the chat. There's been some good questions and keep those coming, partly selfishly because as Tony mentioned, the CFRU project, one of the things that we're doing or hoping or planning to deliver out of that is a set of these FAQs or best practices guidelines for our forest region around here. And these are the great kind of questions like which LiDAR is better than others, what are the requirements for certain resolutions, more specifically, the plot data, what are the character and type and types of things you need to measure in the field to calibrate these models that works better than other ways. So all these kind of comparisons and questions are great. So keep those coming. And awesome. Listen to Dave's answers, not mine, because I don't know what I'm talking about. I didn't realize Dave was going to answer, so I would have just shut up.
Awesome. Thanks, Dan. That's a great point. Okay, so hopefully you can all see my RStudio screen at this point. I could get a thumbs up. Awesome, thanks, Dan. Okay, so all right. The other thing I wanted to mention about this, so I did mention that this is a workflow that is just basically going to demonstrate a LiDAR only approach to EFI. but we'll commonly use optical imagery as well as one of the or some of the covariates that go in to the modeling process. But I would also say that the other thing that we've been doing more recently, and we've been experimenting this with some of our partners, so Seven Islands Land Company and a couple of land trusts out in Rangeley, and then also with Katahdin Forest Management in a pilot project that we're currently working on with them, where we're using a process that, surprise, surprise, the Canadians developed and have shared their code for doing this type of thing. But the idea is, to put in your calibration plots. I apologize for that hiccup. I'm getting a message that my internet connection is unstable, but hopefully, fingers crossed, that'll sort itself out. So that's something that we've been doing more recently, where you use something called principal component analysis, and you run a PCA on the LiDAR point cloud, basically the metrics, the grid metrics from the LiDAR point cloud, and use that to help you decide where to put in your field plots to build the modeling. And I can let Dave speak to more of the particulars of that process. It's kind of beyond the scope of today's seminar. It is fairly complex and a bit cumbersome, the workflow involved. But we did receive some feedback from our partners, Seven Islands and the folks at the Land Trust in Rangeley. And we used, again, that process, and then they went out and measured the field plots with survey grade GPS, fixed radius plots. But we told them, where to put the plots, basically, based on, again, the structure of the point cloud, and achieved some very good results of the EFI. And I believe that was also using the QL2, the state LiDAR. So I'd mention that also as we're thinking about doing this. All right, so I'll just ask again, because I had that message that told me I had an unstable internet connection, but Dan, can you still see my RStudio?
Yep. Yeah, you dropped out for a minute there, froze up, but it wasn't, I think we got.
Okay, great, thank you.
People can follow up with principal components questions later, I'm sure.
Yeah. Okay, so RStudio here, right? And I've already, I'm sure most of you, certainly many of you are well familiar with RStudio. I've already gone ahead and installed my packages. So these are the packages that are required for this workflow. So I'm not going to run that piece of the code. Before the seminar today, I also loaded all of these libraries. So those are all loaded. The packages are loaded and ready to go. So we'll start here where we're going to load the data and generate some LiDAR metrics. So basically, it's very well annotated here as well. And thanks to Dave for developing this workflow and annotating the code. But the first thing you'll do is just run that first line, setting your working directory. So I've got a folder in here for the demo today. You just pick that directory. And then down in the console here, it tells you that's your working directory. So we're all good there. If you have a computer with multiple cores, you can set the code to work with parallel processing. So it'll use, on my workstation, we've got 24 cores. So I'm going to use 12 of those. I could probably stand to use a few more. I believe Dave uses 16 on a 24 core machine. But for the purposes of the demo, I'm just going to leave it at 12. So I go ahead and run that piece of code. to set that. Then I'm going to read the LiDAR tiles for this project and generate what's called a catalog, a last catalog object. So that's next. And that just allows us to work more efficiently. So it will, load the tile that it needs from the catalog, do the processing, pull that out of memory, load the next last tile, do the processing, pull that out. And that will happen across 12 cores on my computer. Okay, so then we're just going to plot an aerial base map here for reference. So now this just shows me it's a good visual check for, hey, so here's my catalog of LiDAR tiles. Is this where I am expecting it to be? And if it's not, then typically, you'll want to look at your LiDAR tiles and just ensure that your projection is correct. If it's not, then you would have to reproject the point cloud data. This is stuff that you would do all up front, of course, just to make sure that everything is set up correctly. So that's a good check. Then I'm going to run this next piece of code, writing the files to disk. So that will typically, if you have a slower computer, that will speed things up a bit. And then I'm going to, the height cutoff here is 2 meters. You can set that to whatever you want, but 2 or 3 meters is typically very common. So we're not looking at any points below 2 meters above ground. And then this next piece of code, we're loading the plot polygons containing the metrics to be modeled. So that's my field plot data, basically, right? And then these next lines of code are just ensuring that all of my fields are numeric. That's important for working through this process in random forest. So that's a good check. And then we'll view this next piece of code, the plot locations within our last catalog. So there they are. You can see within, this is on the PEF. I should mention that, and Dave or Dan, correct me if I'm wrong here, but I believe these LiDAR data, the point clouds, are research grade from a NASA G-LIGHT mission from, I believe, summer 2017. So it's leaf on, and it's dense point cloud, right? So we're talking, 15 or 20 pulses per square meter. So very good LiDAR data for EFI. All right, so that looks good. Then I'm going to clip based on my plots. So that's working now. That's going to take a little while here. I am using 12 cores. You can see in the console, you've got a little stop sign there. So you don't want to hit that because it's currently running. And obviously a little processing meter down here at the bottom telling you how long to complete this part of the process. So we'll just give that a few more seconds. Any questions so far while we're waiting for that to finish?
Yeah, can I put Dave on the spot? I don't know if this was addressed in what you said, Tony. I may have missed it, but Greg Miller asked about how to determine the number and spacing for the ground plots.
So yeah, I actually waited because I know Tony was going into the discussion about principal component analysis and how we're investigating how that could be used to determine where to put your plots. But yeah, that's one of the research questions we're looking at with our CFRU project. How few plots are needed to get really good results, depending on other factors like quality of the LiDAR data and so forth. So We don't have a definite answer to that, but we're hoping to get to that answer as part of this project and be able to recommend an appropriate number of plots given the amount of area that you're looking to apply these models to.
In other words, you can maybe get away with fewer plots if you put them in the right spots.
Correct.
And what the principal components workflow does up front is that it samples through the variation in your LiDAR rather than the traditional way that you would sample through the variation in your inventory data from the ground. So you take advantage of the thing that you're actually modeling from, which is the LiDAR, and you might be able to put those plots in the right places based on analyzing the remote sensing data up front. That's the theory. Like Dave said, we still have to test that.
Yeah, Dan, quick question / comment is, so isn't there any chance that you can actually input the coordinates or like the spatial data, kind of like, and have that like downweighted in the PCA, because there's like, you're selecting points based on the variability you see on the LiDAR, but there's stuff that isn't captured by the LiDAR, right? So, and that's maybe just like, there's like a lot of like, spatial like autocorrelation and whatnot. So you could use the like spatial data itself as, to variables.
Like adding a like a covariance term or something.
Right.
Yeah, I don't know if that's been done. Seems like it should be. I know it's been done in more other optical with Landsat data and things like that people do run variograms on that first. Seems like you could do it with, I guess, Dave, you would, because you run the PCA through the metrics, the gridded metrics already, right? So you could add a spatial term in that. Yeah,
no, absolutely. I mean, we're right now just looking at the LiDAR itself, just kind of building off of what they do up in Canada. They're using this process operationally already, it sounds like. So, but yeah, there's certainly more work to test other things out that can be done.
That's great. Yeah, interesting discussion and interesting concept, Dudu. Yeah, I don't see why you couldn't add, some of those additional metrics that measure covariance and even maybe perhaps spatial autocorrelation in that PCA to try to capture that. Okay, so also down here in the console, you'll see, so we clipped from our last catalog based on the plot data, our field plot data, and it's just giving you a summary there, of the coordinate system and projection, the area, the points, and the density of those points, and then of course number of files. So we've got 127 field plots essentially. So then we run this next bit of code to store that in memory. And then we're going to calculate all of this, what are called the standard metrics. So that's this function here. And this is one of the packages that we loaded at the start of the demo. The LiDAR, LIDR. So that is an R package for working with point cloud data and generating, these height and density metrics from the point cloud. So that's what we're going to calculate now. So we'll run that. And the plot over here in the lower right, basically all of the little red plots are going to slowly change to black. They're being processed. This part of it moves pretty quickly. Okay, and then we're going to merge. So at this point, we're going to merge the field measured inventory attributes with our LiDAR grid metrics, the height and density metrics. for those plots. So we'll go ahead and run this line of code. That creates that new object called D in our example. Then we're going to write, and this guy takes a little bit of time, so I'll get this started. Even with 12 cores on my machine, it doesn't happen instantaneously. So basically now we're writing the standard LiDAR metrics for the entire area of interest, our study area, right? And again, this is over in the Penobscot experimental forest, that research grade, 15 to 20 points per meter, very dense LiDAR, but it's still, moving pretty fast at this stage. So our standard metrics, we're doing this with a 10-meter grid cell. So that's essentially our spatial resolution or ground sample distance. And so we're measuring the point cloud and summarizing based on that cell size. And then we'll get into the actual modeling here in the next few steps. We're going to start with % softwood. I should also mention, just to give you a sense, of how quickly this is moving now, with 12 cores on my workstation in the Wheatland lab. Our workstation, so Dave and I each have a workstation with 24 cores, I believe 128 gigabytes of RAM, of memory. And then, of course, we've got a NAS with, high-speed direct network connection, and also 2 graphics processing units in those workstations. So the point of all that is just to say significant processing power on display in this demo. And then Dave, maybe you could speak a little bit to, this is a small area, right? Just a few thousand acres in the PEF. In your experience, when you run something, that's 100,000 or 200,000 acres, what are we talking about here in terms of time involved to do the modeling process and then apply the modeling to, the wall-to-wall grid metrics?
Sure. So on a computer like what you're using here for the demo and what I have, oh boy, I'd say a couple 100,000 acres would take a couple of days to get through the whole workflow. So yeah, if you're using a lower end computer, you can still do this. It'll just take longer, certainly.
Great. Thanks, Dave. Okay, so that piece is done. So now I'm just going to step through each of the steps for, we'll start with % softwood, and then I'm just going to highlight the rest of the code and run it because you'll do the same set of steps for each of the response variables that you want to model, right? So each of the inventory parameters that you want to model for your area of interest. So with this next command, this next piece of code, we're subsetting only the inventory metric of interest. So we're removing all these others, and column 3 is the % softwood. So we're going to go ahead and run that line, and then these next 3 lines of code, cleaning up the table and getting things ready for random forest. And then after all that pre-processing and data cleaning, this is just to run the random forest model. Boom, we're done. So then we'll create a table of predicted and observed values. And then we'll also in the console here review, sort of the model performance, the standard common model performance measures that we would want to review and know something about. So things like the residuals, coefficients, your R square, so 0.78, well adjusted, yeah, 0.78. All those sorts of things, standard model performance measures. And then with these next lines of code, we've got our model now for percent softwood. And so now we're going to make these predictions. And then we'll plot variable performance. So this is an interesting graph. I'm sure many of you have seen this before, but basically just a graph of model performance. So with percent softwood, intensity is sort of the reflectance intensity of the LiDAR pulses. And so unsurprisingly, when we're modeling percent softwood, intensity shows up as quite important among all of the standard grid metrics based on the plot data that we've used to build this model. Then we're going to use right raster to create the percent softwood raster. Then this next one, we're just going to do a scatter plot of predicted versus observed values for the model. Oh. And that's, I think I'll just go ahead and set all of this and run that. So there we go. We've just got our equation here and basically predicted versus observed for percent softwood. So that's that. Done with percent softwood. We've written our percent softwood raster. So now, just in the interest of time, I want to show you some of the actual results. I'm just going to go ahead and so now we're doing the same thing, the same process for modeling volume. And then generating, the model performance and all of those things. And then we're doing basal area, I believe is next. Yep, we'll do that. And then tree count. Then I'll maybe leave it right there, let that run. So several more plots. Runs pretty quickly. And then this next piece of code, basically model performance across all of our inventory metrics. So we'll go ahead and run those lines of code. And you see them here as well. We're also writing them to a CSV file, so you can make yourself a table for reports and those sorts of things. And then in this last piece of code, this is something that you'd want to be obviously careful about doing. How far can you geographically extend, the validity of a model that you create to another area. And so in this example, we're going to use these models that we've created for the PEF and basically apply them to a LiDAR point cloud data set for the demerit forest. So that's what's happening here. And we'll just run that. And that's something that, is pretty commonly done. But again, you have to be careful. How closely does my forest, the conditions of that forest where I created the model actually apply to, where I want to extend those predictions and create prediction maps using that model for another area, another geographic area. So that's something that you can do, but obviously it's important to consider the validity of that approach. In this instance, certainly the forest types and structures are fairly similar, so we have confidence that we can do this in a legitimate way in this example. Okay, so that is moving along and done. Okay, so lots going on here, but basically you've got these plots. You can look through for the demerit and the models from creating the models on the PEF. So all those are there and available in R. And then the last thing I wanted to show you, and I was just pulling this into ARC. So for example, I've got predictions on the PEF. So things like percent softwood. Get over there to the PF. Percent softwood, basal area, volume, right? And then I can also should be able to look at this as a table, my model performance table. So if I just open this table, based on our models, basically just a nice summary of the R squares for each metric that we're modeling. R squares, root mean square errors, coefficient of variation, mean bias plots or values. All of those are just right there. So that's pretty nice. And then, I can also just look at my demerit predictions, but basically, a similar kind of thing, just for the demerit. Okay, I think I'll leave it there. Any questions or comments? Dave or Dan, anything that I have missed?
No, other than thanks, Tony, for giving us that overview and the workflow. It was great.
Yeah, you bet.
Who's got questions? Who has to just like run out and do this now? Let us know. I'll give you some LiDAR data. Go wild.
All right. Well, thanks everyone. Thanks for joining us.
Thanks, Tony.
You bet.
Good job.
Thank you.
You bet. Thanks, guys.
Thanks, Tony. This was great.